So this is the Arrhenius equation. The rate constant depends on the frequency factor and the activation energy and the temperature. And so we can, the Arrhenius equation shows us here that the rate constant is equal to the frequency factor times e raised to the power negative EA over RT. We can rearrange this by taking the natural log of both sides and get a linear form. Here we can graph the natural log of the rate constant versus 1 over t, and we've got a slope of negative EA over R and an intercept of natural log of A. Now A does depend on the temperature, but its temperature dependence is relatively small, and so it's often just ignored. So let's look at an example of this. The decomposition of ozone shown here is important to many atmospheric reactions. So ozone decomposes into oxygen and an oxygen atom. And we can study those, the kinetics of the reaction. And so here we have, at different temperatures, the rate constant for that reaction. So starting from 600 Kelvin all the way up to 1900 Kelvin. And our task here is to determine the value of the frequency factor and the activation energy for the reaction from those numbers. And the way you do this is you graph the data. Now obviously on an exam you don't really have the correct equipment or technology to be able to graph data like this. I'm not going to make you do that on an exam, but I will make you do it on the worksheet. Okay? And the way you do this is you use a program such as Excel, a spreadsheet. Instead of doing all of this by hand, that's very tedious. So what we want to do is we want to use that linear form of the Arrhenius equation. So the natural log of K is minus EA over R times 1 over T plus natural log of A. So this is what's on the y-axis. This is what's on the x-axis. This is our intercept, and that's our slope, M. So to graph this data, we have to do some math on it first. We'd have to take, pointer's gone? What's up with this? We'd have to take that temperature. It's already in Kelvin, so we don't have to convert it. But we need 1 over the temperature. And we need that rate constant, and we need the natural log of the rate constant. So you would do those calculations and graph the data, and this is the graph you would end up with. So here we have the natural log of K versus 1 over the temperature in kelvins, and we get a nice straight line. It's a little too perfect, but that's okay. And when we use linear regression, we graph this in Excel as well. Linear regression gives us this equation for the line. So here we have y equals minus 1.12 times 10 to the 4th x plus 26.8. So here we have a slope and an intercept. So remember that the y-intercept is equal to what? The natural log of A. A is the frequency factor, right? So if the natural log of A then would equal 26.8, and we need to find that frequency factor. So to get rid of natural log, we do the inverse function. You can't divide by ln. You could try, but it doesn't mean anything. So the opposite of natural log is e to the x. So we would raise each side, e to the power of each side, right? That's taking e to the x of both sides. E to the x, e to the natural log of a is just a. So then we get out our calculator. we've got e to the 26.8. That's giving me 4. We're around to 3 sig figs. 4.36 times 10 to the 11th. It's a really big number. So that's the frequency factor. And then we were also tasked with finding the activation energy. So the slope is equal to negative EA over R. In this case, that is minus 1.12 times 10 to the 4th. And what's R? 8.314 joules per mole Kelvin. That is the ideal gas constant, but we don't want to use the 0.08206 liter atmospheres per mole Kelvin, because then we'll end up with an activation energy in liter atmospheres. So we're going to plug this in down here for R. Well, maybe we should just simplify this a little bit first. Negative EA would equal negative 1.12 times 10 to the 4th times R. Right? Just multiplying R by both sides, or both sides by R. And then those negative signs are a problem, so if we multiply both sides by negative 1, we can get rid of that. Are we okay with that? And now here for R, I'm going to plug this in. So R is 8.314 joules per mole Kelvin. So we get this 1.12 E4 times 8.314 equals, calculator's giving me 93116.8. Now, what are the units on that? We're pretty sure joules should be in there, right? Because it's an energy, right? But what about the mole and the Kelvin? Well, does that slope have a unit? It would be the units of y, the rise, divided by the units of x, the run, rise over run, right? So what the units of y, natural log of something, there's really no units there. But x has the units of 1 over t, 1 over Kelvin. So the units of the slope are 1 over Kelvin, which would be kelvins, right? So this actually has a sign, a unit of kelvins. Let me just, I'll squeeze that in. So that's kelvins. So then the kelvins are actually going to cancel, and we get a unit of joules per mole. And the per mole thing is not unreasonable to show up in a rate, an activation energy. What should we do with how we're representing that answer? We should probably round it a little bit, right? And joules might not be the best unit. Would kilojoules be better? It's a big number, it's 93,000, right? So it's probably better to express this as kilojoules. And so that would be dividing by 1,000. So that would be probably round this and call it 93.1 kilojoules per mole. Yes?
I have 2 questions.
Okay.
What is capital A and why is it significant?
Okay, so capital A is the frequency factor. And we talked about that a long time ago last week. right? And we had this long weekend, and so our brains all returned to mush. The frequency factor has to do with how often or how frequently the reaction approaches the activation energy barrier. Yeah. And this exponential term has more to do with how often or what fraction of the time is it successful in overcoming the barrier.
The 11 on the 10? That?
No,
Oh, that.
yeah, so in K equals A e to the negative EA over RT. This part has to do with the fraction of times that the reaction is successful, and A is the frequency, the rate at which it tries to get over the bump. So, if the frequency factor is larger, if the exponential term here is larger, then the rate constant will be higher, the rate will be faster. Good questions. Anybody else? This business of taking an equation, putting it into the form of a line, y equals mx plus b, and then graphing the data is a very, very common technique in chemistry, and we're going to see it over and over again in this class. So if this is something that you've just like completely erased from your long-term memory, please ask me about it, and it'll come back to you. We'll get it straightened out, but we're going to use it over and over again. So this is not something to just skip over. Yeah?
I have a question. If A is a frequency factor, why doesn't it have a unit in like seconds or minutes?
That's an excellent question. Why doesn't A have a unit? I believe that it does. I believe that it does. Let's think about K, the rate constant. What units does the rate constant have?
Molarity per second.
Molarity per second, sometimes, but the rate is always molarity per second. The rate constant has different units depending on what order the reaction is, right? And so then when we get into an equation like this, the rate constant, we don't know here what order the reaction is, so we can't really say what the units are. So then we're like, well, we'll just skip over it. One of the important things in getting these values correct, because the units are a little sketchy sometimes, you want to make sure that all of your terms are in the regular units for these sorts of calculations. So if you have a temperature, it's got to be in kelvins. If you have an energy, it needs to be in joules when you do the calculation. You got to use R as 8.314 joules per mole Kelvin. If you've got a quantity of matter, it needs to be moles. If there's a volume, it's got to be liters. But that's an excellent question. Any other questions? Yes?
I think I read that the exponential factor is supposed to be between 1 and 0 and 1. Is that right?
Yes.
What is A supposed to be, or can it be anything?
A could be anything. Yeah, so the frequency factor, it can be anything. The exponential term being the fraction of times that it's successful is between 0 and 1. Yeah. And I think we analyzed this a little bit in a previous lecture. When EA is large and temperature is low, then this term will go towards 0. You've got a large hump to get over and very little energy from your temperature to get over it. Reaction's not going to happen. At a low activation energy and a high temperature, this will approach 1. Because the smallest this could get would be 0, right? As this number gets really, really small, then this just gets closer and closer to 0 because it's negative. The exponent's negative. Any other questions? So for the decomposition of ozone reaction in a previous example, use the results of the Arrhenius analysis to predict the rate constant at 298 Kelvin. Well, we need some values there, don't we? We need that 93.1 and the 4.3. Oh, I'm not going to remember that. I'm going to write it on the board. 93.1 kilojoules and 4.36 times 10 to the 11th. There's got to be a better way to do that on my iPad, but I don't know what it is. So we'll just use the whiteboard. Okay, so the results. We're using the results. The results were that EA was equal to 93.1 kilojoules per mole, and that A was 4.36 times 10 to the 11th. So they want us to use those numbers to predict the rate constant at 298. Well, 298 K, that's a temperature, right? Temperature equals 298 Kelvin. What's the equation that links rate constant to activation energy and temperature? The Arrhenius equation? Okay. K is equal to A times E to the negative EA over RT. So what we're going to do is we're going to plug in the activation energy, the temperature, and the frequency factor and find out what K is. So this is going to equal the frequency factor, 4.36 times 10 to the 11th, times E raised to the power of negative EA. We need to be careful here, right? Because we changed the units on this to kilojoules because it gave a nicer answer. Should we use kilojoules in the exponent? No. We need to put that back into joules. So what we could do is we can say, well, 93.1 kilo means 10 to the third. So times 10 to the third joules per mole. That's kind of an on-the-fly converting the unit. And then that's going to be divided by R times T. So R is 8.314 joules per mole Kelvin, and the temperature is 298 Kelvin. And so up here, we're going to have all of our units cancel out. I'm just going to rewrite this down here without the units because that's kind of a mess, isn't it? So this is 93.1 times 10 to the third divided by 8.314 times 298. So getting that in there, not too bad. But now we have to make sure that we communicate properly with the calculator. And that can be another issue all by itself. So you should have your calculators with you, get them out, and make sure that you can tell your calculator the correct thing to do. So I'm using the TI-36X Pro, and so what I'm going to do is I'm going to put in 4.36 EE11 times, and then I'm going to press the E to the X button, and that gives me a parenthesis, and so then I'm going to press minus 93.1 EE3 divided by 8.314, It's also divided by 298, and we'll close the parentheses and press equals. And I get that K equals 2.0891 times 10 to the minus 5. And so we'd probably say, well, it's about 2.09 times 10 to the minus 5. Rate constant has units, but like we discussed earlier, we can't really identify what they are here because we don't know the order of the reaction. Anybody else get that number, or did I screw it? Yeah? Okay. So the Arrhenius equation is great when we've got lots of data. We've measured the rate constant at all these different temperatures, and we can graph the data. What if you don't have the luxury of all that data? Or you don't have the means to do graphing and linear regression? Well, then we can use what's called the two-point form of the Arrhenius equation. So this is taking that linear form and just looking at 2 points. So all we need is an activation energy and temperature at 2 different instances. So if we have 2 temperatures and 1 rate constant, we can calculate the other rate constant, or we could calculate a temperature. So this is the natural log of K2 over K1 is equal to EA over R times 1 over T1 minus 1 over T2. So that's how your book shows it. I find that hard to remember. I don't know about you, but 1s and 2s are easy to reverse, right? So I prefer to think of it this way. So there's K2 over K1, and when we do change in, like delta T, it's always final minus initial. And so this is the second one. You can think of that as the final one over the initial. That's like final minus initial. And then over here, what bothers me about this is it's 1 minus 2. I'd like it to be 2 minus 1. And do you notice that there was a negative sign in the regular equation, right? So I'd prefer to just leave that minus sign in there. And then we've got 1 over T2 minus 1 over T1. So in my mind, this corresponds more closely to this linear form of the equation. Essentially what this two-point form is doing is you take the information at one data point and we're subtracting the information at the other data point. And so that's how we get rid of natural log of A. Any questions about that? So this is the one I'll be using because that's the one I remember. Oops. Oh my goodness. I just hit it once. Okay. Example of using the two-point form. Consider the reaction between nitrogen dioxide and carbon monoxide. The rate constant at 701 Kelvin is measured as 2.51 1 over molarity second, and at 895 Kelvin it's measured as 567. Find the activation energy. And units are specified there, kilojoules per mole. So we've got 2 rate constants, and we've got 2 temperatures, and we can use that to find the activation energy. So I'm going to call the 701 the first set. So T1 is 701 Kelvin, and K1 is 2.57, And then T2, it's important to label these because otherwise you can reverse them by accident and then you get the wrong answer. It's always a bummer. And this is 567. So then we're going to look at that linear form of the equation. The natural log of K2 over K1 is equal to negative EA over R times 1 over T2 minus 1 over T1. Yes?
So that equation, the way that you write it, is the same as the one that the book shows?
Yes. The difference is that the book has factored out the negative 1 from here to cancel that. When you do that, this order switches. But this one makes more sense to me because it follows a pattern. And anytime we can get things to follow a pattern, it makes it easier to remember. You can do it the other way and you'll come up with the same answer. Okay, so one thing that could be tricky in this problem, if they give you temperatures in Celsius or Fahrenheit, heaven forbid, you'd have to remember to change those into kelvins. So we could solve this equation for EA, but because of the fractions and the natural log and everything, that could get ugly really fast. So this is an equation where it's probably best to put the numbers in, simplify the numbers, and then solve for your variable. So we'll write these in here. Natural log of K2, 567 over 2.57. Now, these have units. What happens to the units? They cancel out. So I wrote them in there, but they cancel out. So this is equal to negative EA, that's our variable, divided by R. We need to use the 8.314 joules per mole Kelvin. And then we've got temperature, 1 over T2, 1 over 895 Kelvin minus 1 over 701 Kelvin. Now, depending on how you interact with your calculator, you can just put numbers in and kind of do the rearranging on the fly and come up with the answer, or you might need to write down some intermediate results. So when I ask you to show your work, what am I expecting? I would like to see the written out equation. Sometimes there's a mistake made there, and if you write it out for me, then I can catch it, right? I would like to see the equation, however you've rearranged it or whatever, with the numbers plugged in. Because another place where you can make a mistake is you put K2 in for K1 or something. Now after this, you might not show any work. You could just come directly to the answer for that. But this part here is what I would consider to be the minimum showing your work for this problem, okay? So I'm going to do this problem twice. I'm going to do it just in my calculator, and if you've got a TI-36X Pro and you want to follow along, you can try this. Natural log of 567 divided by 2.57, close parentheses. Then I need to multiply by the 8.314, and I need to divide by the quantity, 1 divided by 895 minus 1 divided by 701, and then I need to change the sign. I'll multiply by -1, and I'm coming up with, write it over here, So that's the number I came up with, just on the calculator. Now let's go through this and write down some intermediate values, because this is probably a more common approach for students. So you probably want to do this math here, 567 divided by 2.57. So you're going to get the natural log of 220.62. Now the thing is, when you're writing down intermediate values here, more digits is better. If you round that to 220 or 221, you might end up with some deviation from this. So write down more than you think is necessary. And so we can't really simplify that part. But I can simplify this term here. 1 divided by 895 minus 1 divided by 701. Now, don't try to do an algebra thing and get common denominators and subtract them out and give me a fraction with whole numbers. Just use your calculator, okay? That's not going to be pretty. So that's giving me minus 0.000309215. See, that's a negative number, and that negative is going to cancel with this negative. So I'm going to cancel out those negatives, and now we could write this out. EA, we're going to multiply by the 8.314, and we're going to divide by the 0.000309215. That's probably more digits than is necessary, times the natural log of 220.62. That's a multiplication sign. So I'm going to type that in and see if I get the same answer. It is essentially the same. Yes?
Does the order matter? Like, wouldn't you first divide by the zero, like divide the natural log by 0.0003 and then multiply it by...
That's an excellent question. Does the order matter here? Shouldn't you take this and divide it by that and then multiply by that? The order doesn't matter, because you can, when you're multiplying, you can just rearrange the terms. The dividing is important, and it's important to make sure that you're dividing by the 0.00 number instead of the 8. But so doing it this way, my calculator is giving me 145,094,0708. So a little bit different. Is that difference significant? No. So we're supposed to express this in kilojoules per mole. I didn't include all the units in this showing my work part here, but if we go back to this one, pointer's not working again. Okay, if we go back to this one, let's look what happens with the units here. Here we have 1 over Kelvin, and here we have 1 over Kelvin. So those kelvins are going to cancel out. And so we've got joules per mole here. That's going to be the unit on EA. So this guy right here is, joules per mole. And that's the same for this one over here. It asks us to express it in kilojoules per mole. So convert to kilojoules, we'll divide by 1,000. So that'll move the decimal point over here. And what would be a reasonable number of significant figures? Probably 3. So that would give us 145 kilojoules per mole. And if I round this one to 3 significant figures, what do I get? The same, 145 kilojoules per mole. So then the next question here, use the results from the previous example and the given rate constant of the reaction at either of the two temperatures to predict the rate constant for this reaction at 525 Kelvin. So in the previous example, we were given rate constants at two different temperatures, and we used that to calculate the activation energy. Now we're trying to find the rate constant at a third temperature. So we're going to use the two-point form of the Arrhenius equation again. So natural log of K2 over K1 equals negative EA over R times 1 over T2 minus 1 over T1. And we determined that EA was equal to 145 kilojoules per mole. We've got a temperature here. We're going to have to call that T1 or T2. And then we have to pick one of the other temperatures and rate constants. So I'm just going to pick the first one. We had 701 Kelvin and 2.57 molarity of the -1 seconds to the -1. There's just no good way to say that. So this is a temperature and this is a rate constant. So I'm going to be solving for a rate constant in here. And I'm going to look at that and say, you know, it'd be easier to solve for K2 because it's in the numerator. So I'm going to solve for K2, and that means that this is T2 up here, and I'm going to call this T1 and K1. You get to choose which is 1 and which is 2. They just have to be paired up correctly. So again, with this being a messy equation, I'm going to plug the numbers in and then we'll figure out how to solve. So natural log, I've got K2 divided by K1, 2.57, that mess is equal to, now I've got the activation energy. This is what we calculated. Is kilojoules an okay unit there? No, it needs to be in joules. Ideally, we'd go back and use a couple more digits, but nobody has time for that today. So we're going to call this 145 times 10 to the third joules per mole. And if you want to, you know, do it the other way and say, well, that's 1.45 times 10 to the fifth joules per mole, that's fine. Then I've got R, 8.314 joules per mole Kelvin, and that's the thing that's making me use joules. And then I've got my temperatures, 1 over T2, which is 525 Kelvin, minus 1 over T1, 701 Kelvin. So on the right side of the equal sign, I've just got numbers. I don't have any variables, right? So we can find out what the right side of the equation is equal to. So negative 145 EE3 divided by 8.314 times, and I'm going to use parentheses, open parentheses, 1 divided by 525 minus 1 divided by 701, close parentheses. And this is giving me negative 8.3405 and some other stuff. all these units canceled out. Any questions so far? So that you can see what I'm doing here, I'm just going to rewrite that. So the natural log of that ratio of rate constants is equal to negative 8.3405. So how do I get rid of natural log? E to the x, right? So K2 over 2.57 is going to equal e to the minus 8.3405. So to get K2 by itself, I'm going to find this, and then I'm going to multiply by 2.57. I'm getting K equals, I'll put that in scientific notation, 6.13 times 10 to the minus 4. Any questions? Yeah.
All these equations, do we have to memorize them for the test, or are they gonna?
That's an excellent question. Excellent question. Do we have to memorize these? I can't quite remember if I gave them to you on the Chapter 14 exam or not. I suspect that I did give you just like this whole list of equations, a mess of equations. What I would encourage you to do, though, is when you're working problems, try to come up with the equation from memory and then check it against the book or your notes. Because that'll help you to just be more familiar with it. I'm pretty sure, though, I gave you a list of equations, but that's an excellent question. Because the most important thing here is that you can solve the problem. The goal here is not, can you memorize a bunch of combinations of letters, right? Because what do we do in real life? We remember constants and equations that we use all the time. And the other ones, we remember that they exist, and we figure out where to look them up, right? Any other questions? Yes?
I get confused when it's like the negative, the units with the negative exponent on the bottom. I thought when it's on the bottom, you can get rid of the negative, you know what I'm saying?
Oh, here?
Yeah.
You could bring these units up here and say that this product or quotient, whatever it is, that thing together has units of molarity times seconds. But then over here, when we solve for K, we're going to have to bring the units back.
Okay.
And what's happening here is that the units of K2 and the units of K1 cancel each other out.
Okay.
Yeah.
So to make them put them on the top if you wanted them to be positive?
Yes.
Okay.
Yeah, because these units with the negative exponent, that's the same as 1 over molarity times second, which is a weird unit, but it comes from the rate laws. Any other questions? You can see that there's a lot of places that you could make a tiny mistake and get a wrong answer. And that's why some of the questions on the exam are write out your work problems. And those will be the ones more like this where there's a lot of calculating to do, because if you just, messed up on a minus sign or something, I'd like to give you partial credit for it instead of you just giving it. Because, so you did some of the math wrong. You got here and then you screwed up somehow. well, you deserve like at least 3/4 credit or so for doing all the hard stuff, and you just screwed up on some math. You do need to lose points though, because screwing up on the math is screwing up, right? Details do matter. You know, you type in your password that's case sensitive and you've got a capital instead of a lowercase and it won't let you in, right? You send an email and you get one letter wrong, it doesn't go through, right? And sometimes that's really significant. Okay. The collision model. So let's look at that frequency factor and talk a little more about what it means. So we're going to look at a reaction that has two reactants in the gas phase. So remember kinetic molecular theory of gases. Gases move in straight lines, and the particles, until they run into something, right? And their kinetic energy is related to the temperature. Temperature is the average kinetic energy of the particles. Some of the particles will have higher energy and some lower. So what that means is some of the particles are moving faster and some are moving slower. So a chemical reaction between these two particles will occur after a sufficiently energetic collision between the two molecules. In order for the molecules to react, they have to come in contact with each other, right? If they're on opposite sides of the container, they can't react. So they have to come in contact with each other, and there has to be enough energy in that collision to overcome the activation energy. So each approach to the activation barrier is a collision between reactant molecules. So we've got these molecules, and they're just zinging around in this container. There's going to be a lot of collisions, but only some of them are going to be successful. So the frequency factor is usually less than the number of collisions per second. Any ideas why? They're not all successful. So inside the frequency factor, which we've just been calling A, there are actually hiding two more variables, an orientation factor and the collision frequency. So activation energy is part of the problem, but orientation is also an issue. The two particles have to collide with the correct orientation. So the orientation factor is also a fraction of collisions. It's a fraction that have a favorable orientation between 0 and 1. So if all the collisions have the correct orientation, that factor would be 1. The collision frequency is the number of collisions per unit time, typically about 10 to the 9th per second under regular sorts of conditions. So these things are bumping into each other a lot, right? 10 to the 9th times in a second. So we can take this K equals A, e to the minus EA over RT, and we can break A down into P times Z. So you could say that A is equal to P times Z. Orientation factor and a collision frequency. Any questions? So let's look at the orientation factor. So the molecules have to be correctly oriented in order for them to react. So here we're looking at this specific reaction. NOCl plus NOCl gives 2NO plus Cl2. So when these react, to react, they have to collide in the correct way. If they collide here with the oxygens bumping into each other, that's not going to work. Doesn't matter how hard they hit, it's not going to cause a reaction. If you have your chlorine bumping into the oxygen, also not going to work. This is only going to react when the chlorines collide with each other. When the chlorines collide, a bond can form between the two chlorine atoms. The bonds between the chlorine and the nitrogen break, and you end up with this up here. Does that make sense? So they have to collide in the right order, orientation. And so you've got these molecules, and they're zinging through space, and they're probably rotating as well. And so how do you predict whether the collision is going to be the correct orientation or not? For this particular reaction, they can measure that orientation factor and find that it's 0.16. That's kind of low, right? Only 0.16 or 16% of the collisions have the correct orientation. So when you have a small orientation factor, it means that the molecules have to be aligned in a very specific way. Some collisions are very particular about orientation, others are not. If you have an interaction between two atoms, then the orientation factor is usually approximately 1, because atoms are spherical, they're three-dimensionally symmetric, and so you can't hit the wrong side of an atom, right? They're all the same. So two atoms colliding, the orientation factor is going to be 1. But the more complicated the molecule gets, probably the lower the orientation factor gets. Could you have an orientation factor that's larger than 1? No. You wouldn't think so, right? But this says it is possible. So if the orientation factor is greater than 1, what that means is that you don't actually need a collision. It could happen without a collision. Okay? You're like, wait, what? It's not going to be a big deal.